Hello there, and welcome to the Drowsy Inquirer. I'm so glad you found your way here tonight, because we're about to drift through something you carry with you every single moment of your life, yet something no one has ever fully understood. Tonight, we're exploring time. Wherever you are in the world right now, let this be your invitation to slow down. Let your shoulders drop. Let your jaw unclench. Let your thoughts settle like dust in a quiet room, each particle catching the last light before stillness takes over. Time is strange. It is the one thing we all share, and yet no two people experience it the same way. A minute can feel like an hour when you are waiting, and an hour can vanish like a breath when you are lost in something beautiful. It stretches, it compresses, it bends in ways that even the greatest minds in physics are still trying to understand. Tonight, we will wander through the story of time from every angle we can reach. We will begin with the way your own brain experiences this very second, and then we will pull back layer by layer until we are gazing across billions of years and asking questions that have no easy answers. We will visit ancient sundials and atomic clocks, forests that keep records in their rings, and stars whose light left home before the Earth existed. We will sit with Einstein for a while, and we will wonder what it means that the universe may not even need time at all. Some of what you hear may surprise you. Some may feel like remembering something you always quietly knew, and some may simply float past like clouds seen from a window, soft and unhurried and easy to let go. If this kind of gentle curiosity brings you comfort or helps you drift off to sleep, consider leaving a like or subscribing. It helps other restless minds find their way here too, one quiet night at a time. But for now, take a slow breath. Let your eyes close whenever they're ready. And let's begin this long, unhurried journey through the most mysterious dimension of all. Your brain is living in the past. Right now, as you listen to these words, your mind is not experiencing the present moment. Not truly. Every signal from the outside world, whether it is light hitting your eyes, sound entering your ears, or the texture of your blanket against your skin, takes time to travel through your nervous system, be processed, and assembled into the seamless experience you call now. That delay is roughly 80 milliseconds. It does not sound like much, but it means that the present, as you perceive it, has already happened by the time you become aware of it. Your brain is not showing you a live broadcast of reality. It is showing you a carefully edited replay, stitched together so smoothly that you never notice the lag. Every conversation, every sunrise, every moment you have ever called right now was, in the strictest sense, already the past. And yet it feels immediate. It feels real. Perhaps that is the first hint that time is not quite what we assume it to be. Even at its most intimate, even inside your own skull, it is already doing something unexpected. Time slows down when you're afraid. If you have ever been in a car that brakes suddenly, or tripped and felt yourself falling, you may remember the strange sensation that everything seemed to move in slow motion. For decades, scientists wondered whether the brain actually speeds up during moments of fear, processing the world faster than usual. A neuroscientist named David Eagleman tested this by having volunteers fall from a 50-meter tower into a safety net while wearing a special wristwatch designed to flash numbers just slightly too fast for normal perception. If fear truly accelerated the brain's clock, they should have been able to read those numbers during the fall. They could not. Their brains were not actually running faster. What was happening was something more subtle. During frightening moments, the amygdala kicks into high gear and begins recording far more detail than usual. More sensory data gets encoded. More memory gets written. And when you look back on that moment, the richness of the memory makes it feel as though it lasted much longer than it did. Time did not slow down. Your memory just became denser, and your brain mistook that density for duration. This is a gentle reminder that your experience of time is not a clock ticking on the wall. It is a story your brain tells you, shaped by emotion, attention, and surprise. Childhood summers felt endless for a reason. Think back to being 7 or 8 years old if you can. A single summer afternoon could stretch out like a continent. The walk to a friend's house felt like a voyage. A week at a grandparent's home seemed to last a month, and now years pass like flipping pages. Where did all that time go? The answer lies in how your brain encodes novelty. When you are a child, nearly everything is new. The first time you taste something, the first time you visit a place, the first time you hear a song, your brain creates rich, detailed memories for each experience. Those dense clusters of memory make the past feel expansive when you look back on it. But as you grow older and your days begin to follow familiar patterns, your brain becomes more efficient. It stops recording every detail of your morning commute or your 100th Tuesday at work. Routine compresses time. This is why travel to unfamiliar places often makes a week feel longer, and why a year spent doing something entirely new can feel more spacious than 5 years of repetition. Your brain measures time not in seconds, but in new experiences. The more first times you collect, the longer your life will feel when you look back on it. In a way, seeking wonder is a way of stretching time itself. Your body contains hundreds of tiny clocks. You have probably heard of the circadian rhythm, that internal cycle that tells you when to feel sleepy and when to feel alert, roughly synchronized with the 24-hour rotation of the Earth. But what you may not know is that this rhythm is not controlled by a single master clock. It is an orchestra. Deep inside your brain, a small cluster of about 20,000 neurons called the suprachiasmatic nucleus acts as the conductor. It receives light signals from your eyes and uses them to keep the whole system in sync. But nearly every cell in your body has its own molecular clock, running its own roughly 24-hour cycle. Your liver cells have a clock tuned to when you eat, while your skin cells have a clock that influences when they repair themselves. Your heart, your kidneys, your immune cells, all of them are quietly keeping time. In 2017, the Nobel Prize in Physiology or Medicine was awarded to Jeffrey Hall, Michael Rosbash, and Michael Young for uncovering the molecular mechanisms behind these clocks. They found that specific genes produce proteins that accumulate during the day and degrade at night, creating a feedback loop as reliable as any pendulum. You are not just a being that moves through time. You are a being made of time, hundreds of tiny rhythms ticking together inside you right now. Jet lag is your cells arguing about what time it is. When you fly across several time zones, the light outside suddenly disagrees with what your body expects. Morning arrives when your internal clocks say it should still be midnight. Your brain adjusts relatively quickly within a day or two because it receives direct light signals from your eyes. But the rest of your body does not adapt so fast. Your digestive system, your hormonal cycles, your temperature regulation, each of these systems resets at its own pace. Some organs take 3 or 4 days, others may take over a week. During that in-between period, your body is essentially experiencing multiple time zones at once. Your brain might say it is morning, but your gut still thinks it is the middle of the night. Your muscles may be ready for action while your immune system is running on a schedule from 3 days ago. This is why jet lag is not just about being tired. It is a kind of internal temporal chaos. Dozens of clocks drifting out of sync with each other. And yet, given a few days of consistent light and routine, they all find their way back to harmony. Your body wants to agree on what time it is. It just needs a little patience. A second used to be a very different thing. For most of human history, the second was defined by the rotation of the Earth. One full rotation was a day divided into 24 hours, each hour into 60 minutes, each minute into 60 seconds. It seemed perfectly logical. The Earth's spin was the most reliable clock anyone could imagine, but it was not reliable enough. Scientists discovered that the Earth's rotation is not constant. It wobbles. It slows down over centuries due to tidal friction from the moon. Some days are microseconds longer or shorter than others. For everyday life, this does not matter, but for fields like physics, telecommunications, and satellite navigation, even the tiniest inconsistency could cause problems. So in 1967, the scientific community made a quiet but extraordinary decision. They redefined the second. Instead of basing it on the turning of a planet, they based it on the behavior of a single atom. Specifically, a second is now defined as the duration of exactly 9,192,631,770 oscillations of radiation emitted by a cesium-133 atom. That number is not poetic, but it is astonishingly precise. The atom does not wobble, does not tire, and does not care about the moon. Time, at its most fundamental, human-measured level, now rests on the shoulders of something smaller than a grain of dust. You spend more time in darkness than you realize. The average person blinks about 15 to 20,000 times a day. Each blink lasts somewhere between 100 and 400 milliseconds. If you add all of those tiny blackouts together, you spend roughly 10% of your waking hours with your eyes closed, and you almost never notice. This is because your brain performs a remarkable trick. It fills in the visual gaps. During each blink, your visual cortex essentially freezes the last image it received and holds it steady until the eyes open again. The result is a seamless, unbroken experience of seeing. You never perceive the flicker. You never notice the missing frames. Your brain edits them out in real time, like a film editor removing every moment the camera blinked. What this tells us is something quietly profound. Your conscious experience of the world is not a raw recording. It is a curated version, assembled from fragments and smoothed over with assumptions. Time, as you feel it, is partly constructed. Your brain decides what to show you and what to skip. And it does this so well that you go through your entire life believing you see everything, when in truth, you are always missing more than you know. The oldest clock humanity ever used is the sky. Long before gears or pendulums, long before numbers were scratched into stone, our ancestors measured time by looking up. The sun rose in one direction and set in another, marking a single day. The moon swelled from a sliver to a glowing disk and back again, marking a month. And the stars shifted slowly across the sky, completing their great rotation once a year, marking the turning of seasons. These rhythms shaped everything: when to plant, when to harvest, when to migrate, when to celebrate. The sky was the first calendar, and it was available to everyone everywhere, for free. Some ancient structures seem to have been built as enormous sky-reading instruments. Stonehenge in England aligns with the solstice sunrise. The Passage Tomb at Newgrange in Ireland allows a beam of light to enter its inner chamber only on the winter solstice. The Egyptians aligned the Great Pyramid with extraordinary precision to true north, using the stars as their guide. These were not simple people making rough guesses. They were careful observers who watched the sky for generations and encoded what they learned into stone. Time was not abstract to them. It was written in light and shadow, in moonrise and starfall. And in a way, every clock we have built since then is simply trying to keep up with the sky. A shadow was once the most trusted timekeeper. Before electricity, before springs and gears, before even the simplest mechanical device, there was the sundial, a stick in the ground, a shadow moving across the earth, and suddenly you had a way to divide the day into parts. The earliest known sundials date back to ancient Egypt, around 1500 BCE, though the concept is almost certainly older. The idea was elegant in its simplicity. As the sun moves across the sky, the shadow cast by a vertical object, called a gnomon, rotates predictably. By marking where the shadow falls at different times, you can read the hours simply by glancing at the ground. What makes a sundial remarkable is that it cannot be wrong, not in the way a mechanical clock can. It has no batteries to die, no springs to wind down, no gears to misalign. The shadow moves because the earth turns, and the earth turns because the laws of physics say it must. A sundial is not so much a device as it is a direct, physical manifestation of a planet rotating in space. Of course, sundials have limitations. They do not work at night, they do not work on cloudy days, and they read slightly different times depending on where you are on the globe. But for thousands of years, a shadow on the ground was the most honest answer anyone could give to the question, what time is it? Water measured time before gears ever could. Somewhere around 1500 BCE, long before anyone thought of clockwork, ancient civilizations found a way to measure time using nothing but the slow, steady drip of water. These devices, known as clepsydras, were among the first clocks that could work regardless of the sun. Day or night, cloudy or clear, the water flowed and time was marked. The simplest version was just a bowl with a small hole in the bottom. Water would drain out at a roughly constant rate, and markings on the inside of the bowl showed how much time had passed. More sophisticated versions, especially those designed in ancient Greece, Egypt, and China, used floats connected to pointers or cascading bowls that triggered mechanisms at regular intervals. In ancient Athens, water clocks were used in courtrooms to ensure that each speaker received a fair amount of time. In Persia, elaborate water clocks were used to determine the exact moment for irrigation. In China, the polymath Su Song built a water-powered astronomical clock tower in the 11th century that stood over 30 feet tall and tracked the movements of stars and planets. There is something quietly beautiful about measuring time with water. A drip, then another, then another. Each one identical, each one gone the moment it falls. Time itself made visible in the patient rhythm of something as simple as a drop. Monks shaped the modern clock without meaning to. In the medieval monasteries of Europe, time was not a convenience. It was a sacred duty. Monks were required to pray at specific intervals throughout the day and night, following a schedule known as the canonical hours: matins before dawn, lauds at first light, prime, terce, sext, none, vespers, compline, each one fixed to a particular part of the day. And the trouble was knowing exactly when those hours arrived, especially in winter, when the sun was unreliable, or at night when sundials were useless. Candle clocks and water clocks helped, but they were imprecise. The need for something better drove the development of the first mechanical clocks, sometime in the late 13th century. These early devices were not the elegant timepieces we imagine. They were large, heavy tower-mounted contraptions powered by falling weights. They had no minute hands, sometimes no faces at all. Instead, they simply rang a bell at regular intervals, calling the monks to prayer. But the invention changed the world far beyond the monastery walls. Once mechanical clocks appeared in town squares, public life began to organize around them. Market hours, work shifts, school schedules, all of it gradually became anchored to the steady tolling of a clock. A technology born from quiet devotion ended up reshaping civilization. The pendulum gave time a heartbeat. In the late 16th century, a young Galileo Galilei sat in the Cathedral of Pisa and watched a chandelier swing. Whether the arc was wide or narrow, the chandelier seemed to take the same amount of time to complete each swing. He timed it against his own pulse. The period of the pendulum, he realized, was constant. This observation lay dormant for decades. But in 1656, the Dutch scientist Christian Huygens built the first true pendulum clock, using this principle to regulate the movement of gears. The result was a revolution in timekeeping. Before the pendulum, mechanical clocks could drift by as much as 15 minutes a day. With it, the error dropped to about 15 seconds. For the first time, time had a visible, physical rhythm. The steady swing of the pendulum, back and forth, became the heartbeat of households, of observatories, of entire cities. The tick and the tock entered human consciousness. Clocks were no longer just practical tools. They became companions. They sat on mantels and hung on walls, and their sound filled rooms with a gentle pulse that people found, and still find, strangely soothing. There is something almost alive about a pendulum in motion, a weight, a wire, and the quiet pull of gravity repeating a single gesture endlessly. It asks for nothing. It simply swings. And in that swinging, time becomes visible. Trains forced the world to agree on what time it was. Before the 19th century, every town kept its own time. Noon in London was not noon in Bristol, which was not noon in Edinburgh. Each city set its clocks by the sun, which meant that the further west you traveled, the later noon arrived. When the fastest way to move between cities was by horse, this did not matter. The differences were small, and nobody needed to coordinate their minutes. Then the railways came. Suddenly, people and goods were moving between cities at speeds that made those few minutes matter enormously. A train leaving London at precisely 2 o'clock might arrive in a town whose clock said it was 10 minutes earlier. Scheduling became chaotic. Passengers missed connections. And in a few cases, confusion over timetables contributed to accidents. In 1847, British railway companies adopted Greenwich Mean Time as their standard. Gradually, towns across Britain synchronized their clocks to match. And in 1884, delegates from 25 nations gathered in Washington, D.C. for the International Meridian Conference, where they agreed to divide the world into 24 standardized time zones, all referenced to the prime meridian at Greenwich. It was not an act of science. It was an act of coordination. For the first time in human history, strangers thousands of miles apart could look at their clocks and agree that it was the same minute of the same hour. Time, once a purely local experience, became global. And it all began because trains needed to run on time. Atomic clocks lose 1 second in 300 million years. After the pendulum, after quartz crystals, after every mechanical and electrical improvement the 20th century could offer, scientists reached the ultimate timekeeping device, the atomic clock. It works by tuning into the natural vibrations of atoms, specifically the cesium-133 atom, which oscillates at an extraordinarily precise and consistent frequency. The first accurate cesium clock was built in 1955 at the National Physical Laboratory in England by Louis Essen and Jack Perry. It could keep time to within 1 second over several hundred years. Modern cesium clocks, refined over decades, can maintain accuracy to within 1 second in roughly 300 million years. This is not just impressive engineering. It is the foundation of modern civilization in ways most people never realize. Every time you use a GPS device, your location is calculated using signals from satellites, each carrying an atomic clock. Every time you make a phone call, send an email, or stream a video, atomic time synchronization keeps the data flowing in the right order. Financial markets, power grids, air traffic control, scientific research, all of it depends on clocks that do not drift. We built a civilization that moves at the speed of light, and we anchored it to the vibration of an atom. There is a strange kind of poetry in that, the tiniest thing we know, keeping time for the largest systems we have built. There are clocks even more precise than cesium. As remarkable as cesium clocks are, a new generation of timekeepers has surpassed them. Optical lattice clocks, developed in the early 21st century, use atoms of elements like strontium or ytterbium, trapped in grids made of laser light. Instead of measuring microwave frequency oscillations like cesium clocks, with these devices measure oscillations at optical frequencies, which tick far more rapidly, hundreds of trillions of times per second. The result is staggering precision. The best optical lattice clocks built so far would not gain or lose a single second even if they had been running since the Big Bang, 13.8 billion years ago. They are so sensitive that they can detect the difference in the flow of time between 2 points separated by just a few centimeters of altitude, because gravity affects time differently at different heights. This level of precision is not just about telling time. It opens the door to entirely new kinds of measurement. Scientists are already discussing whether optical clocks could be used to detect gravitational waves, map the interior of the Earth by measuring tiny variations in gravity, and/or even redefine what we mean by a second. We have crossed a threshold. Time is no longer something we merely read. It is something we can feel, almost touch, with instruments so fine that the curvature of space itself becomes visible in their readings. Time is not the same everywhere. This is one of the most startling truths in all of physics, and it was discovered not by looking outward at the stars, but by a man sitting quietly and thinking. In 1905, Albert Einstein published his special theory of relativity, and among its many consequences was this: time does not flow at the same rate for everyone. If you are moving faster, your time runs slower compared to someone standing still. This is not a trick of perception. It is not about clocks being built poorly. It is a fundamental feature of the universe. And the speed of light in a vacuum is always the same, about 300,000 kilometers per second, no matter how fast you're moving. For this to be true, something else has to give. That something is time. As your speed increases, time itself, as measured by any clock you carry, stretches out. Seconds become longer. Minutes expand. At everyday speeds, the effect is immeasurably tiny. You will not notice it on your walk to the kitchen or your drive to work. But at speeds approaching the speed of light, the effect becomes dramatic. A clock on a spacecraft traveling at 90% the speed of light would tick at less than half the rate of a clock left on Earth. This is not a theory waiting for proof. It has been confirmed in countless experiments. And it means that right now, this very second, the time is flowing at slightly different rates in every moving object around you. Time is not a river with one current. It is an ocean, and every traveler sails through it at their own pace. Astronauts come home younger than they should be. The effects of time dilation are not just theoretical. They are measurable, even for humans. Consider the case of Scott Kelly, a NASA astronaut who spent 340 consecutive days aboard the International Space Station. The station orbits the Earth at roughly 28,000 kilometers per hour. At that speed, time for the astronauts on board ticks just slightly slower than for people on the ground. When Scott Kelly returned to Earth, he was approximately 5 milliseconds younger than his identical twin brother, Mark Kelly, who had stayed behind. 5 milliseconds. It is an almost absurdly small number, barely a flutter, but it is real. It was measured. And it means that Scott Kelly literally traveled into his brother's future by the tiniest of steps. Every astronaut who has ever orbited the Earth has experienced this. Sergei Krikalev, who spent a cumulative 803 days in space, is estimated to be about 22 milliseconds younger than he would have been had he never left the ground. He has, in a very real sense, time traveled. These are not dramatic numbers. You will not come back from space to find the world unrecognizably changed. But the principle behind them is profound. Time is personal. It depends on where you are, how fast you are moving, and how strong the gravity around you is. Your life is not synchronized with anyone else's. It never was. Gravity bends time just as surely as speed does. 10 years after his special theory of relativity, Einstein went further. In his general theory of relativity, published in 1915, he showed that gravity is not simply a force pulling objects together. It is a curvature of space-time itself. Massive objects like planets and stars warp the fabric of space and time around them, and this warping affects how quickly time passes. The stronger the gravitational field, the slower time flows. This means that a clock at the base of a tall building, runs very slightly slower than a clock at the top, because the lower clock is closer to the center of the Earth and therefore deeper in its gravitational well. The difference is extraordinarily small, but it has been measured with atomic clocks. In 2010, researchers at the National Institute of Standards and Technology used optical clocks to detect time dilation across a height difference of just 33 centimeters. 1 foot of altitude was enough to change the flow of time. This means that your feet age more slowly than your head, by an amount so tiny it would take billions of years to add up to a noticeable difference. But the fact remains, time is not uniform, even across the length of your own body, and on larger scales, the effect becomes dramatic. Near the surface of a neutron star, where gravity is incomprehensibly strong, time slows by a measurable fraction. Near a black hole, it slows even more. The universe does not have a single clock. It has an infinite number of clocks, each one ticking at its own rate, shaped by the mass and motion around it. When Einstein's theory runs quietly inside your phone, every time you open a map on your phone and watch that small blue dot land precisely on your street, you are witnessing Einstein's theories at work. The global positioning system relies on a constellation of satellites, each carrying an atomic clock, orbiting the Earth at about 20,000 kilometers above the surface. Your phone calculates your position by measuring the tiny differences in the time signals received from several of these satellites. But here's the problem. Those satellites are moving at high speed, which means their clocks tick slightly slower due to special relativity. At the same time, they are farther from the Earth's gravitational center, which means their clocks tick slightly faster due to general relativity. The two effects do not cancel out. The gravitational effect is larger, so the net result is that the satellite clocks gain about 38 microseconds per day compared to clocks on the ground. 38 microseconds does not sound like much, but light travels about 11 kilometers in that time. Without corrections for relativity, GPS positions would drift by roughly 10 kilometers every single day. Your phone would tell you that you are in the middle of a lake when you are actually standing in your kitchen. So every GPS receiver in the world applies relativistic corrections every second continuously. Einstein's equations, scribbled on paper over a century ago, are now running silently in billions of pockets, guiding people home. A clock on the surface of the sun would fall behind yours. Imagine placing a perfectly accurate clock on the surface of the sun and another identical clock here on Earth. If you could somehow watch them both, you would notice that the clock on the sun ticks more slowly, not because it is broken, not because of the heat, but because the sun's gravity is so much stronger than Earth's that it warps the flow of time more deeply. Over the course of a single year, the clock on the sun would fall behind the clock on Earth by about 66 seconds. A full minute lost, simply because of where it sits in the gravitational landscape of our solar system. This is not a thought experiment. It is a direct prediction of general relativity confirmed by decades of precision measurement. And it applies not just to the sun, but to every object with mass. The more massive the object, the deeper it bends the fabric of time around it. Jupiter slows time more than Mars. A white dwarf slows it more than Jupiter. A neutron star slows it more still. You live in a gentle gravitational valley shaped by a modest planet orbiting a middle-aged star. And even here, time bends, softly, invisibly, but undeniably. You are always swimming through curved time, though you cannot feel the current. Near a black hole, time nearly stops. Of all the objects in the universe, none warp time as dramatically as a black hole. A black hole is what remains when a massive star collapses under its own gravity, compressing all of its mass into an impossibly small point called a singularity. Around that point, and the fabric of space-time curves so steeply that nothing, not even light, can escape once it crosses the boundary known as the event horizon. But before that boundary, something eerie happens to time. As you approach the event horizon, time, as measured by a distant observer watching you, begins to slow down. Your movements would appear to stretch out, your words would seem to drag. If they could somehow watch a clock strapped to your wrist, they would see its hands crawling slower and slower, approaching but never quite reaching the event horizon. From your perspective, though, nothing would seem unusual. Your watch would tick normally. Your heart would beat at its usual pace. You would feel no stretching, no slowing. The difference is entirely relative. So time flows at one rate for you and at a completely different rate for someone watching from far away. At the event horizon itself, time, as seen from outside, effectively stops. A photon of light emitted from that boundary would be infinitely redshifted, stretched beyond detection. To the outside universe, you would freeze in place, your image growing dimmer and redder, fading slowly into nothing. This is not science fiction. It is the mathematics of general relativity, tested and confirmed in less extreme conditions across decades of observation. Black holes are not just holes in space, they are holes in time. The twin paradox is not a paradox at all. Einstein's theories led to a famous thought experiment. Imagine two identical twins. Now, one stays on Earth while the other boards a spacecraft and travels at nearly the speed of light to a distant star and back. When the traveling twin returns, she finds that her sister has aged far more than she has. Perhaps decades have passed on Earth, while only a few years passed on the ship. This scenario, known as the twin paradox, troubled physicists for years. If all motion is relative, why should one twin age less than the other? The answer lies in the fact that the situation is not truly symmetrical. The traveling twin accelerates, turns around, and decelerates. She changes reference frames. The twin on Earth does not. That asymmetry breaks the apparent paradox and confirms that the traveling twin genuinely experiences less time. And this is not just theory. We have confirmed it with particles. Muons, unstable subatomic particles created when cosmic rays strike the upper atmosphere, provide a natural test. A muon at rest decays in about 2.2 microseconds. At that rate, even moving at nearly the speed of light, muons should decay long before reaching the Earth's surface. But they do reach the surface in large numbers, because their high speed causes time to dilate for them. From our perspective, their internal clocks are running slow. They live longer, not because they are different, but because time itself treats them differently. The twin paradox is real, time is personal, and the universe keeps different books for different travelers. Moons arrive when they should not. Let us stay with those moons for a moment longer, because their story is one of the most elegant confirmations of time dilation ever observed. Moons are created high in the atmosphere, typically at altitudes of about 15 kilometers, when high-energy cosmic rays from deep space collide with air molecules. A moon's average lifetime is just 2.2 microseconds. Even traveling at 99.9% the speed of light, a muon should only be able to cover about 660 meters before decaying. That is far short of the 15-kilometer journey to the surface. And yet, detectors on the ground record muons in abundance. They arrive by the thousands every minute. How? Because time for the muon is not the same as time for us. At 99.9% the speed of light, time dilation stretches the muon's internal clock by a factor of roughly 22. What feels like 2 microseconds to the muon corresponds to about 44 microseconds in our frame of reference. That is more than enough time at its speed to cover 15 kilometers and reach the ground. The muon does not know it is living longer. From its own perspective, it lives exactly as long as it always does. But the distance it needs to travel appears contracted. It is the same physics, seen from two different angles. Both perspectives are valid, both are real, and both confirm that time is not a fixed stage on which events play out. It is part of the performance itself. Trees write their own diaries in wood. Now let us leave the world of physics for a while and visit a quieter kind of time. The time written in wood. If you have ever looked at the cross-section of a fallen tree, you have seen its rings. Each ring represents 1 year of growth. A wide ring means a good year, plenty of rain, warm temperatures, abundant sunlight. A narrow ring means hardship, drought, cold, or disease. By reading these rings, scientists can reconstruct the climate of a region going back thousands of years. This science is called dendrochronology, and it is remarkably precise. Because trees in the same region experience the same weather, their ring patterns match. By overlapping the patterns of living trees with those of old timber and ancient logs preserved in bogs or ruins, researchers have built continuous tree ring records stretching back more than 12,000 years in some regions. These records have revealed volcanic eruptions that dim the sky, droughts that toppled civilizations, and cold spells that lasted decades. A single tree can carry the memory of 1,000 years within its trunk, written not in words but in the patient accumulation of cellulose, one ring at a time. There is something deeply calming about this. A tree does not rush. It does not skip ahead. It simply grows. And in growing, it keeps a faithful record of every year it has lived. If you ever want to hold time in your hands, find a piece of old wood and count the rings. Ancient corals reveal that days used to be shorter. Deep in the fossil record, there is a chapter of Earth's history written not in wood but in coral. Fossilized corals from the Devonian period, roughly 400 million years ago, show fine growth lines that record daily and seasonal cycles, much like tree rings, but at a finer scale. And when scientists counted those lines, they found something astonishing. A year in the Devonian had about 400 days. The days were not 24 hours long. They were closer to 21.5 hours. The Earth was spinning faster then, completing more rotations in each orbit around the Sun. Over hundreds of millions of years, the planet has been gradually slowing down, and the days have been stretching out. The reason is the Moon. The gravitational interaction between the Earth and the Moon creates tides, and those tides act as a gentle brake on the Earth's rotation. Energy is transferred from the spinning Earth to the orbiting Moon, causing the Moon to drift slowly outward while the Earth's spin decelerates. This process has been going on for billions of years, and it continues today. So the 24-hour day is not a fixed feature of the planet. It is a snapshot, a single frame in an enormously slow film. Millions of years from now, days will be even longer, and the Moon will be even farther away. The rhythm of your life, waking and sleeping, sunrise and sunset, is built on a tempo that is always, imperceptibly, slowing down. The Earth's days are still getting longer. The process that stretched those ancient Devonian days has not stopped. It is happening right now, beneath the surface of your awareness, in the quiet friction between ocean and rock. Every century, the length of a day increases by about 2.3 milliseconds. It is an almost absurdly small amount. No one alive will ever feel the difference. But over geological time, it adds up. 600 million years ago, a day lasted only about 21 hours. 1.4 billion years ago, it may have been as short as 18 hours. This gradual slowing has practical consequences, even today. Because atomic clocks keep perfect time while the Earth does not, the two systems slowly drift apart. To keep our official clocks aligned with the planet's actual rotation, scientists occasionally add a leap second to coordinated universal time. Between 1972 and 2016, 27 leap seconds were added. Each one was a tiny acknowledgement that the Earth is no longer quite as punctual as it used to be. And so, even as you lie still tonight, the Earth beneath you is spinning just a fraction more slowly than it did last night. The day you live today was, by an amount too small to measure with any human sense. The longest day in the history of the planet so far. Tomorrow will be longer still. Time is stretching. 1 millisecond at a century, and the universe is in no hurry at all. A fly sees you in slow motion. Not all creatures experience time the way you do. For a housefly, the world moves at a very different pace. The key lies in something called the flicker fusion rate, which is the speed at which an animal's visual system can process individual flashes of light. For humans, this rate is roughly 60 frames per second. Anything faster than that, and the flashes blur together into smooth, continuous motion. This is why films and video, which typically run at 24 to 60 frames per second, look seamless to us. But a fly's flicker fusion rate is about 4 times higher, around 250 frames per second. This means a fly can perceive individual moments that would be a blur to you. When you swing your hand toward a fly, from the fly's perspective, your hand is moving in slow motion. It has ample time to calculate a trajectory and leap away. This is not about intelligence. It is about temporal resolution. The fly's brain processes visual information far more rapidly than yours, which means its subjective experience of each second is richer in detail. In a very real sense, a fly experiences more moments per second than you do. Different animals inhabit different speeds of time. A snail's flicker fusion rate is much slower than a human's, so the world may appear to it as a rapid blur. A pigeon's rate is faster than ours, making it a superb aerial navigator. Each species lives in its own temporal bubble, tuned by evolution to the pace its survival requires. Hummingbirds live in a faster world. Consider the hummingbird. Its heart can beat more than 1,200 times per minute. Its wings flap up to 80 times per second. It can rotate its wings in a figure-8 pattern, hover in midair, and even fly backward, all while tracking the precise position of a flower's nectar with absolute accuracy. To accomplish these feats, the hummingbird's nervous system must process information at extraordinary speed. Its perception of time is almost certainly faster than ours, each second filled with more sensory data, more decisions, more reactions. What feels like a single moment to you might feel like several to a hummingbird, and yet the hummingbird's lifespan is measured in just a few years. Some species live as long as 10 years, but many live only 3 to 5. In those brief years, their hearts will beat billions of times. Their wings will complete hundreds of millions of strokes. They will visit thousands of flowers and migrate across continents. If you measure a life not in calendar years, but in heartbeats or experiences, the hummingbird may live just as fully as any creature on Earth. It simply does so at a different tempo, faster, brighter, and more intense. A whole lifetime compressed into a flicker, burning with quiet urgency. Some sharks alive today were born before Shakespeare. In the cold, dark waters of the North Atlantic and Arctic Oceans, a creature glides through the depths at a pace that makes even the slowest land animal look hurried. The Greenland shark moves at less than 3 kilometers per hour. It grows only about 1 centimeter per year, and it may live for more than 500 years. In 2016, a study published in the journal Science used radiocarbon dating of proteins in the eye lenses of Greenland sharks to estimate their ages. The oldest individual in the study was estimated to be approximately 392 years old, with a margin of error that placed her potential age as high as 512. If that estimate is correct, this shark was born sometime around the year 1500. The Renaissance was unfolding in Europe. Leonardo da Vinci had recently painted the Mona Lisa. Shakespeare had not yet been born. The colonization of the Americas was just beginning, and somewhere beneath the Arctic ice, a small shark began its slow, patient journey through the centuries. She is still swimming, still gliding through the same cold waters, unchanged, unhurried, while above the surface, entire civilizations have risen and fallen. She does not know what a century is. She simply lives, one slow heartbeat at a time, carrying half a millennium in her body like a quiet secret. Bristlecone pines have watched civilizations come and go. High in the White Mountains of Eastern California, at altitudes above 10,000 feet, grow some of the oldest living things on Earth. The Great Basin bristlecone pines are gnarled, wind-sculpted trees that cling to dry, rocky slopes where almost nothing else survives. They are not tall, they are not lush, but they are ancient. The oldest known bristlecone pine, a tree named Methuselah, is over 4,800 years old. It was a seedling when the Great Pyramid of Giza was being built. It was already centuries old when Moses is said to have led the Israelites out of Egypt. Or it has stood in the same spot while the Roman Empire rose and fell, while the Dark Ages gave way to the Renaissance, while humans learned to fly and then to leave the planet entirely. And there is another bristlecone whose exact location is kept secret to protect it. That may be even older, possibly exceeding 5,000 years. These trees survive not despite their harsh environment, but because of it. The cold, dry conditions slow their growth to a crawl, but they also prevent rot and disease. Their wood is so dense and resinous that even dead bristlecones can remain standing for thousands of years after they stop growing. To stand beside a bristlecone pine is to stand beside a living record of time. Every twist in his trunk, every strip of bark still clinging to weathered wood, is a testament to patience. It does not rush. It does not compete. It simply endures quietly while the world turns around it. Some creatures can press pause on time itself. In the microscopic world, there lives a creature so resilient that it has survived conditions that would destroy almost anything else. The tardigrade, sometimes called a water bear, is a plump, eight-legged animal barely half a millimeter long. It lives in moss, in soil, in ocean sediment, in fresh water. And when its environment becomes hostile, it does something extraordinary. It stops. Through a process called cryptobiosis, a tardigrade can expel nearly all the water from its body, curl into a tiny barrel-shaped structure called a ton, and reduce its metabolic activity to less than 1% of normal. In this state, it is neither alive nor dead. It does not eat, breathe, or grow. Time, for the tardigrade, effectively pauses. In this suspended state, tardigrades have survived temperatures near absolute zero and well above the boiling point of water. They have endured the vacuum of space, intense radiation, and pressures 6 times greater than those found in the deepest ocean trenches. Some tardigrades have been revived after spending 30 years in a dried state in a laboratory. When conditions improve and water returns, the tardigrade rehydrates, unfolds, and resumes its life as if nothing happened. It picks up exactly where it left off. There is something wonderfully defiant about this. A creature so small you need a microscope to see it, facing the harshest conditions the universe can offer, and responding by simply waiting. Not fighting, not fleeing, just pausing patiently until the world becomes gentle again. Deep time is almost impossible for the human mind to grasp. The Earth is 4.54 billion years old. Written as a number, that is 4,540 million years. You can read those words. You can understand them intellectually, but truly feeling what they mean is another matter entirely. Here is one way to try. Stretch your arms out to either side as far as they will reach. Let the tip of your left middle finger represent the formation of the Earth, and the tip of your right middle finger represent this exact moment. The entire span, fingertip to fingertip, is 4.54 billion years of Earth's history. On that scale, the age of the dinosaurs occupies a strip about the width of your forearm. The entirety of human existence, from the first Homo sapiens to this very night, fits within the thickness of a single fingernail at the tip of your right hand. And all of recorded history, every empire, every invention, Every war, every poem, every song could be erased by one gentle stroke of a nail file. Deep time is humbling, not because it makes us small, but because it reveals how much has happened before us. Continents have drifted, oceans have opened and closed, entire ecosystems have risen, flourished, and vanished, all in the long, quiet stretch of time that came before a single human eye ever opened. For billions of years, the Earth had no oxygen to breathe. Imagine stepping outside on a warm summer day, taking a deep breath, and filling your lungs with air. That simple act, so effortless, so automatic, is only possible because of an event that took place over 2 billion years ago. For the first half of Earth's existence, the atmosphere contained almost no free oxygen. The air was thick with nitrogen, carbon dioxide, methane, and water vapor. But oxygen, the gas that powers nearly all complex life today, was virtually absent. The early Earth was an alien world by any standard we would recognize. Then slowly, a group of tiny organisms called cyanobacteria began to change everything. These microscopic creatures developed the ability to photosynthesize, using sunlight to split water molecules and release oxygen as a waste product. At first, the oxygen they produced was absorbed by iron dissolved in the oceans, forming vast deposits of rust-colored rock known as banded iron formations. But eventually the oceans became saturated and oxygen began to accumulate in the atmosphere. This event, known as the Great Oxidation Event, occurred roughly 2.4 billion years ago. It was catastrophic for most of the life that existed at the time, anaerobic organisms for which oxygen was toxic. But it opened the door for an entirely new kind of life. Aerobic metabolism, powered by oxygen, is far more efficient than its predecessors. Without it, complex multicellular life, animals, plants, fungi, everything you know, would never have been possible. Every breath you take tonight is a gift from ancient bacteria that lived and died in an ocean that no longer exists, under a sky that looked nothing like the one above you now. Complex life appeared remarkably late in Earth's story. For most of Earth's history, life was simple. Single-celled organisms, bacteria, and archaea dominated the planet for over 3 billion years. Whereas they built stromatolites, formed vast mats on the ocean floor, and slowly reshaped the chemistry of the atmosphere. But for all their success, they remained microscopic. Complex, multicellular life, the kind you can see with the naked eye, did not appear until astonishingly late. The Cambrian explosion, the sudden burst of biodiversity that produced the ancestors of most major animal groups alive today, began roughly 540 million years ago. That is less than 12% of Earth's total history. If the planet's existence were compressed into a single day, complex animals would not appear until after 8:30 in the evening. Before the Cambrian, there were the Ediacaran organisms, soft-bodied creatures that left faint impressions in ancient seafloors. Some looked like quilted discs. Others resembled ferns or fronds anchored to the ocean bottom. They were the first large, complex life forms, but most of them left no descendants. They were an experiment, a quiet rehearsal before the main performance. What triggered the Cambrian explosion remains one of the great questions in biology. Rising oxygen levels, new ecological niches, the evolution of eyes and predation, all of these may have played a role. But what is certain is that for billions of years, life was patient. It waited, changed slowly, and then, in a geological instant, it bloomed. Dinosaurs ruled the Earth for far longer than humans have existed. When we think of dinosaurs, we often imagine them as ancient failures, creatures that had their time and then vanished. But in truth, the dinosaurs were one of the most successful groups of animals the planet has ever seen. They dominated terrestrial ecosystems for roughly 165 million years, from the late Triassic to the end of the Cretaceous. To put that in perspective, modern humans, Homo sapiens, have existed for about 300,000 years. The dinosaurs reigned for approximately 550 times longer. If the age of the dinosaurs were a single year, human existence would occupy the last 4 hours and 45 minutes of December 31st. During their long reign, dinosaurs evolved into an extraordinary range of forms. There were armored tanks like Ankylosaurus, long-necked giants like Argentinosaurus, feathered hunters like Velociraptor, and flying reptiles that soared on wingspans wider than a small airplane. They colonized every continent, including Antarctica, and at least one lineage survived the extinction event that ended the Cretaceous, evolving into the birds that sing outside your window today. The next time you hear a bird, you are hearing an echo of a dynasty that lasted longer than we can easily imagine. They did not fail, they thrived, and a small branch of their family tree is still here, still flying, still singing. More time separates Stegosaurus from T-Rex than T-Rex from you. Here is a fact that quietly rearranges your sense of time. The Stegosaurus, with its bony plates and spiked tail, lived during the late Jurassic period, roughly 155 to 150 million years ago. Tyrannosaurus rex, the most famous predator in history, lived during the late Cretaceous, roughly 68 to 66 million years ago. The gap between them is about 84 million years. The gap between T-Rex and you, reading this tonight, is about 66 million years. Stegosaurus was more ancient to T-Rex than T-Rex is to you. The two iconic dinosaurs never met. They never shared a landscape. They were separated by a chasm of time so vast that entire ecosystems rose and fell between them. Mountain ranges formed, oceans shifted, continents drifted into new configurations, and new species of dinosaurs evolved, flourished, and went extinct, all in the space between these two animals that we so casually place side by side in children's books. This is what deep time does. It stretches the familiar until it becomes strange. It reveals that even within a single chapter of life's story, the pages are so numerous that no human mind can hold them all at once. The entire universe can be compressed into a single calendar year. In 1977, the astronomer Carl Sagan introduced a beautiful way of visualizing the history of the universe. He called it the cosmic calendar. Imagine compressing all 13.8 billion years of cosmic history into a single calendar year, beginning on January 1st and ending at midnight on December 31st. On this scale, the Big Bang occurs at the first moment of January 1st. The Milky Way forms around March 20th. Our sun and solar system do not appear until September 1st. Life on Earth begins around September 21st. But complex multicellular life does not emerge until mid-December. Dinosaurs appear on December 25th and go extinct on December 30th. The entire history of Homo sapiens begins at roughly 10:30 in the evening on December 31st. The invention of agriculture happens at 11:59 and 46 seconds. The Roman Empire, the Renaissance, the Industrial Revolution, the World Wars, the moon landing, the invention of the internet, all of it takes place in the final second of the final minute of the final day. You are living in the last flicker of the cosmic year. Everything you have ever known, every person who has ever lived, every civilization that has ever built anything, all of it fits within a single tick of the cosmic clock. This is not meant to make you feel insignificant. It is meant to make you feel the weight of the moment. Right now, in this slender fraction of the universe's story, you are here. You are awake. You are listening. And that is extraordinary. The universe itself is 13.8 billion years old. This number, 13.8 billion years, is not a guess. It is one of the most precisely measured quantities in all of science, and it comes from an unexpected source, the faint glow of the universe's own birth. Shortly after the Big Bang, the universe was a dense, hot soup of particles and radiation. Photons could not travel far without scattering off charged particles. The universe was opaque, like the inside of a thick fog. But about 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Suddenly, photons could travel freely. Light was released in every direction, and it has been traveling ever since. That ancient light, now stretched by the expansion of the universe into microwave wavelengths, fills every cubic centimeter of space. It is called the cosmic microwave background radiation, and it was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, who initially thought they were hearing noise from pigeon droppings on their antenna. By studying the tiny variations in this ancient glow, scientists have calculated the age of the universe with remarkable precision. The latest measurements from the Planck satellite place it at 13.798 billion years, give or take about 21 million years. You are bathed in this light right now. It passes through you, through the walls around you, through the air you breathe. It is the oldest light in existence, a whisper from the very beginning, still traveling, so still arriving, still quietly telling the story of how everything began. Looking at the stars is looking back in time. When you look up at the night sky, you are not seeing the universe as it is right now. You are seeing it as it was. Every point of light in the sky is a message from the past, traveling at 300,000 kilometers per second, but still taking time to reach you. The moon, our closest celestial neighbor, is about 1.3 light seconds away. So the moonlight you see left the moon's surface just over a second ago. The sun is about 8 light minutes away, meaning that if the sun disappeared this instant, you would continue to see it shining for another 8 minutes before the sky went dark. The nearest star beyond the sun, Proxima Centauri, is about 4.2 light years away. Its light has been traveling for over 4 years to reach your eyes tonight. Sirius, the brightest star in the sky, is about 8.6 light years away. The light you see from Sirius left its surface before some of the children born today were conceived. In the Andromeda Galaxy, the most distant object visible to the naked eye is roughly 2.5 million light years away. When the light now entering your eyes left Andromeda, our ancestors were just beginning to walk upright on the plains of Africa. No human language existed. No fire had been tamed. The light was already old before humanity was young. Every time you look at the night sky, you are reading a history book written in light. Each star is a different page, each galaxy a different chapter, and the deeper you look, the further back in time you see. Some photons reaching your eyes are older than the Earth. The light from the most distant objects we can observe has been traveling for more than 13 billion years. The earliest galaxies detected by the James Webb Space Telescope emitted their light when the universe was only a few 100 million years old, a cosmic infant by any measure. Those photons left their sources roughly 9 billion years before the Earth even existed. They crossed expanding voids of space, passed through dust clouds, threaded between galaxies, and eventually, after a journey longer than the age of our planet, arrived here. Some of them landed on the mirror of a telescope. Some of them simply passed through the atmosphere and vanished into the ground. And some of them right now are passing through you. Not in any way you can feel, but they are there. On ancient travelers completing a journey that began before our sun ignited, before our solar system condensed from a cloud of gas and dust, before the atoms in your body were forged in the hearts of earlier stars. You are standing at the end of a beam of light that has crossed the observable universe. The photon does not know you are here. It does not know it has arrived. But for one brief instant, the oldest light in the cosmos and the newest thought in your mind occupy the same point in space. That is a kind of miracle, quiet, invisible, and happening all around you, every moment of every night. Physics does not know why time moves forward. Here is something that may surprise you. The fundamental laws of physics, The equations that describe how particles interact, how forces operate, how energy transforms, almost all of them work equally well in both directions of time. If you filmed two billiard balls colliding and then played the footage in reverse, both versions would obey Newton's laws perfectly. There is nothing in the mathematics that says one direction is correct and the other is not. And yet time clearly moves in one direction for us. Eggs break but do not unbreak. Ice melts but does not spontaneously refreeze in a warm room. We remember the past but not the future. Something is choosing a direction, but the deepest equations of physics do not seem to contain that choice. This is known as the arrow of time, and it remains one of the most profound unsolved problems in physics. We experience time as a one-way street, always moving from past to future, from order to disorder, from cause to effect. But the microscopic laws governing the atoms and particles that make up everything do not share this preference. They are time-symmetric. They do not care which way the clock runs. So where does the arrow come from? The leading answer points not to the laws of physics themselves, but to a single, quietly powerful principle. One that governs the behavior of large collections of particles. One that you encounter every day without ever naming it. Entropy is the compass that gives time its direction. The second law of thermodynamics states that in any closed system, entropy, a measure of disorder or the number of possible arrangements of a system, tends to increase over time. A neat stack of papers left alone on a windy desk will scatter. A hot cup of tea will cool to room temperature. A sandcastle will crumble. These are not coincidences. They are expressions of a deep statistical truth. There are vastly more ways for things to be disordered than to be ordered. If you shuffle a deck of cards, the chance of them landing in perfect sequence is astronomically small, not because it is forbidden, but because there are so many more disordered arrangements available. Nature does not choose disorder on purpose. It simply follows probability, and probability overwhelmingly favors entropy. This is what gives time its arrow. The reason a broken glass does not leap back together is not that the laws of physics prevent it, but that the precise coordination required for every molecule to reverse its trajectory simultaneously is so improbable as to be effectively impossible. It could happen. It is not forbidden. But you would have to wait longer than the age of the universe to see it. So when you watch smoke rise and disperse, when you feel warmth leaving your hands on a cold night, when you notice that things tend to fall apart rather than come together, you are witnessing the arrow of time, not written in the equations of motion, but emerging from the quiet mathematics of chance. Time moves forward because there are more ways to be tomorrow than there are ways to be yesterday. The smallest meaningful moment is unimaginably brief. If you try to divide time into smaller and smaller pieces, you might expect that you can keep going forever, slicing each moment into thinner and thinner slivers without limit. But physics suggests there is a floor, a smallest meaningful unit of time below which the very concept of duration loses its meaning. This unit is called the Planck time, and it is approximately 10 to the power of negative 43 seconds. Written out, that is a decimal point followed by 42 zeros and then a 1. It is so short that no human technology could ever come close to measuring it directly. The Planck time is derived from three fundamental constants of nature: the speed of light, the gravitational constant, and the reduced Planck constant from quantum mechanics. It represents the time scale at which quantum gravitational effects are expected to dominate, the regime where our current understanding of physics breaks down. Below the Planck time, the familiar concepts of space and time may no longer apply. The smooth fabric of space-time that Einstein described might dissolve into something else entirely, a foamy, fluctuating quantum structure that no existing theory can fully describe. Think of it this way: if reality were a digital photograph, the Planck time would be the size of a single pixel in the dimension of time. You cannot zoom in further. You cannot find a smaller piece. It is the resolution limit of the universe itself. And yet, within every single second you experience, there are more Planck times than there are seconds in the entire history of the cosmos. In the quantum world, time does not always flow in one direction. At the scale of atoms and subatomic particles, the rules of time become strange. In quantum mechanics, many fundamental processes are time-symmetric, meaning that the equations describing them work identically whether time runs forward or backward. When two electrons scatter off each other, the interaction obeys the same laws in reverse. When a photon is absorbed and re-emitted by an atom, the process looks the same played backward. At this tiny scale, nature does not seem to have a preferred direction of time. There are rare exceptions. Certain particle decays involving the weak nuclear force violate time symmetry, a phenomenon known as CP violation, first observed in 1964 with kaon particles. But even this violation is subtle and limited. The vast majority of quantum interactions treat past and future as interchangeable. This has led some physicists to suggest that the arrow of time is not a fundamental feature of the universe, but an emergent one, arising only when vast numbers of particles interact together. A single water molecule does not know whether it is part of an ice cube melting or an ice cube forming. It is only when trillions of molecules act together that the direction becomes apparent. Time's arrow in this view is not built into the fabric of reality. It is a pattern that emerges from complexity, like a wave emerging from the motion of countless individual drops of water. Time might not be a fundamental part of reality. This is perhaps the most unsettling idea in all of modern physics. Some of the deepest thinkers in the field have suggested that time, as we experience it, may not be a basic ingredient of the universe. It may instead be something that emerges from more fundamental structures, the way temperature emerges from the motion of molecules, or the way wetness emerges from the behavior of water. The Italian physicist Carlo Rovelli, one of the founders of loop quantum gravity, has argued that at the most fundamental level, the equations describing reality do not contain a time variable. What we perceive as the flow of time may be a consequence of our limited perspective, our inability to see the full quantum state of the universe all at once. In this view, the universe does not happen. It simply is. All moments exist simultaneously, and the sensation of moving from one to the next is an artifact of how our brains process information. Time is not a river carrying us forward. It is more like a landscape, and we are travelers who can only see one small patch at a time, creating the illusion of movement. This does not mean time is not real to us. It means it may be real in the way a rainbow is real, genuine, visible, meaningful, but not a physical object you can touch. It is a perspective, a way of organizing experience, and it may be the most beautiful illusion the universe has ever produced. One of the deepest equations in physics has no time in it at all. In 1967, the physicists John Wheeler and Bryce DeWitt derived an equation that attempted to describe the quantum state of the entire universe. The Wheeler-DeWitt equation is one of the most important and most puzzling formulas in theoretical physics, and it contains no variable for time. This was not an oversight. It was a consequence of trying to combine quantum mechanics with general relativity. In general relativity, time is not a fixed background. It is part of the dynamic fabric of space-time, bending and stretching with matter and energy. When you try to quantize this framework, to apply the rules of quantum mechanics to space-time itself, time does not fit in the way you might expect. It vanishes from the equation. The result is deeply strange. The Wheeler-DeWitt equation describes a universe that is, in a mathematical sense, timeless. It does not evolve. It does not change. It simply exists all at once, in a superposition of all possible configurations. If this equation is correct, then the flow of time, the sense that one moment follows another, must emerge from within the equation rather than being imposed from outside. Time is not the stage on which quantum gravity performs. It is part of the performance itself, and perhaps not the most fundamental part. We do not yet have a complete theory of quantum gravity. The Wheeler-DeWitt equation may be only a stepping stone to something deeper, but its message is striking. At the very bottom of reality, where physics reaches its most fundamental level, time may not be there waiting for us. Philosophers have asked whether only the present moment truly exists. The question of what is real in time has troubled thinkers for thousands of years. Two of the oldest and most enduring answers stand in direct opposition. Presentism holds that only the present moment is real. The past no longer exists. The future does not yet exist. The only thing that truly is now. This feels intuitively correct. The past is gone. But you cannot reach out and touch yesterday. The future has not arrived. All you ever truly have is this single, thin slice of time. But eternalism, sometimes called the block universe view, disagrees. In this framework, all moments in time are equally real. The past is not gone. It still exists, just as a place you are not currently visiting still exists. The future is not unborn. It is already there, waiting in the same way that a page later in a book already exists, even if you have not read it yet. You simply have not arrived at it yet. Einstein's relativity lends surprising support to eternalism. Because time flows at different rates for different observers, two people can disagree about which events are simultaneous. What is now for you may be past or future for someone moving at a different speed. If the present moment were the only real thing, whose present would we choose? There is no consensus. Science alone cannot settle this debate because it involves questions about the nature of existence itself. But it is worth sitting with the possibility, if only for a moment. Perhaps everything that has ever happened and everything that ever will happen is, in some quiet way, still here. Not lost, not yet to come, just somewhere else in the landscape of time. The sun will continue to shine for another 5 billion years. Our star, the sun, has been burning for approximately 4.6 billion years. It is roughly halfway through its life on the main sequence, the long, stable phase during which a star fuses hydrogen into helium in its core. It has enough fuel to continue for roughly another 5 billion years. That number, 5 billion years, is so vast that it can feel almost like forever. But the sun will not remain exactly as it is for all that time. Gradually, as it burns through its hydrogen, it will grow brighter and hotter. In about 1 billion years, the sun's luminosity will have increased enough to dramatically alter Earth's climate. The oceans will begin to evaporate. The planet's surface will become inhospitable to life as we know it. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin fusing helium. It will swell into a red giant, its outer layers expanding beyond the orbit of Mercury and Venus, possibly reaching the current orbit of Earth. Eventually, it will shed those outer layers into space, forming a glowing shell called a planetary nebula. What remains will be a small, dense core known as a white dwarf, about the size of Earth but with the mass of the sun, slowly cooling over trillions of years. This is not a catastrophe. It is a life cycle. Every star is born, lives, and eventually transforms. The sun's story is not one of destruction, but of change. And the atoms it releases in its final breath will drift through space, eventually becoming part of new stars, new planets, perhaps new forms of life. Stars will eventually stop being born. Right now, the universe is a lively place. New stars are forming in vast clouds of gas and dust scattered throughout galaxies. Gravity pulls matter together. It heats up, ignites, and a new star begins to shine. This process has been going on for over 13 billion years, but it will not continue forever. The raw materials for star formation, the great reserves of hydrogen gas, are finite. The galaxies are slowly using up their supplies. Some gas is locked away in stars that burn for billions of years. Some is expelled into intergalactic space by supernova explosions and stellar winds. And some simply becomes too diffuse to collapse. Current estimates suggest that the rate of star formation in the universe has already peaked. It was highest about 10 to 11 billion years ago. Today, new stars are forming at roughly one-third the peak rate. In about 100 trillion years, give or take, the last stars will form, burn through their fuel, and fade. After that, the universe will enter what astronomers call the degenerate era. The only stellar remnants will be white dwarfs, neutron stars, and black holes, slowly cooling, slowly fading. No new light will ignite. The galaxies, once ablaze with billions of stars, will go dark, one by one like candles being blown out in a very large room. This is not a violent ending. It is a quiet dimming. The universe will not explode or collapse. It will simply grow darker, more still, more silent. And even in that silence, the laws of physics will continue, patiently, for timescales that make the current age of the universe seem like a single breath. Even matter may not last forever. The atoms that make up your body, the chair beneath you, the planet you rest upon, these feel permanent, solid, enduring. But some theories in physics suggest that even the most fundamental building blocks of matter may eventually decay. Protons, the positively charged particles at the heart of every atom, are extraordinarily stable. No proton has ever been observed to decay, but several grand unified theories, which attempt to merge the electromagnetic, weak and strong nuclear forces into a single framework, predict that protons are not truly eternal. They may decay with a half-life of around 10 to the power of 36 years or longer. That number is so large that it has no practical meaning in everyday life. Even over the entire current age of the universe, the chance of any given proton decaying is vanishingly small. But on the timescales of the far future, when the last stars have long since faded and the universe has grown cold and dark, proton decay becomes significant. If protons do eventually decay, then over unimaginable stretches of time, all ordinary matter will slowly dissolve. Every atom, every molecule, every remnant of every star and planet will eventually break apart into lighter particles and radiation. Or the universe will lose its substance, not in a dramatic explosion, but in a slow, quiet unraveling. Nothing would be left but a thin soup of electrons, positrons, neutrinos, and photons, drifting through an ever-expanding void. Matter, the stuff of everything we have ever touched or seen, would become a memory written in the trajectories of particles too sparse to ever meet again. Black holes will be the last object standing. In the far, far future, after the stars have all died, and ordinary matter has begun its slow dissolution, one type of object will endure longer than anything else in the universe: black holes. A black hole is, in some sense, the ultimate safe. Nothing that crosses its event horizon can return. It is a region of space-time so warped that it traps everything, including light, within its boundary. And because nothing can escape, a black hole is extraordinarily long-lived, but not eternal. In 1974, Stephen Hawking showed theoretically that black holes emit a faint glow of radiation, now called Hawking radiation. This radiation carries away energy, which means the black hole slowly loses mass. Over time, it shrinks, and eventually, after an almost inconceivable span of time, it evaporates entirely. For a black hole with the mass of our Sun, this process would take roughly 10 to the power of 67 years. For the supermassive black holes at the centers of galaxies, with masses millions or billions of times that of the sun, evaporation would take around 10 to the power of 100 years, a 1 followed by 100 zeros. These are timescales that dwarf everything else in this story. The current age of the universe is not even a rounding error compared to the lifetime of a supermassive black hole, and yet even these titans will eventually fade. The last black hole in the universe will emit its final quantum of Hawking radiation and vanish, leaving behind nothing but a faintly warm patch of empty space. The universe may end not with a bang, but with silence. There is a scenario for the ultimate fate of the universe that is not dramatic, not violent, not sudden. It is called the heat death, and it is in many ways the quietest ending imaginable. Heat death occurs when the universe reaches a state of maximum entropy, when all energy has been evenly distributed across all of space. There are no temperature differences left to drive any process, no stars to generate light, no chemical reactions to sustain change, no gradients of any kind. The universe is in perfect equilibrium, and in perfect equilibrium, nothing happens. Time, in a technical sense, would still pass. The laws of physics would still hold. But without change, without events, time would have no meaning. There would be nothing to mark its passage, no clock to tick, no observer to notice. The universe would simply exist, vast, uniform, and still, like an ocean with no waves, stretching in every direction without boundary or feature. This is not expected to happen for an almost unthinkable span of time, far beyond even the evaporation of the last black holes. It is the final chapter of a story that began with the unimaginable heat and density of the Big Bang. And yet, there is a strange kind of peace in it. Not emptiness, not loss, just stillness. The universe, after all its fire and fury, all its galaxies and stars and life, will finally rest. And perhaps that is not an ending at all, but the deepest kind of quiet. Even in the idea of endings, there is something gentle. We have just traveled through some of the most extreme timescales the universe has to offer, from proton decay to black hole evaporation to the heat death of everything. These ideas might sound bleak if spoken quickly, but sit with them for a moment and something else emerges. The universe does not end in catastrophe. It does not shatter or scream. It fades, gently, gradually, like the last note of a song held so long that you cannot tell when it stopped and silence began. The stars do not explode all at once. They wink out one by one over trillions of years. Matter does not disintegrate in a flash. It dissolves, particle by particle, over time scales that make eternity feel like an afternoon. There is something almost reassuring in this. The universe, for all its power, for all its vastness, chooses the softest possible exit. It does not fight the end. It drifts toward it, the way you might drift towards sleep on a night like this, slowly, peacefully, without resistance. And in the meantime, between now and that distant stillness, there is everything. Every sunrise, every conversation, every heartbeat, every wonder. The universe is in no rush to finish its story, and neither should you be. Every culture has dreamed about the nature of time. Long before clocks and equations, human beings looked at the world around them and tried to make sense of time. And the stories they told reveal as much about the human spirit as they do about time itself. And the ancient Greeks had two words for time. Chronos referred to sequential, measurable time, the ticking of hours, the counting of days. But kairos meant something different. It referred to the right moment, the opportune time, the instant when something meaningful aligns. Chronos is the clock on the wall. Kairos is the moment you fall in love, the breath before a decision, the pause when everything changes. In Hindu cosmology, time is cyclical. The universe passes through vast ages called yugas. each one lasting hundreds of thousands of years, repeating in an endless cycle of creation, preservation, and dissolution. A single day of Brahma, the creator, lasts 4.32 billion years, eerily close to the actual age of the Earth. The Aboriginal Australians speak of the dream time, or the dreaming, a framework in which the past, the present, and future coexist. The ancestral beings who shaped the land are not gone. They are still present, embedded in the landscape, in the stories, in the songs that have been passed down for tens of thousands of years. Each of these traditions captures something that science alone cannot quite express. That time is not just measurement, it is meaning, it is rhythm, it is story. And every human culture, no matter how distant or different, has felt the need to give it a name. One of history's deepest questions about time was asked 16 centuries ago. In the 4th century, a North African bishop named Augustine of Hippo sat down to write his Confessions, a deeply personal work of philosophy and faith. And in Book 11, he posed a question that has echoed through the centuries. What then is time? If no one asks me, I know. If I wish to explain it to one who asks, I do not know. It is a disarmingly honest admission from one of the greatest thinkers of the ancient world, and it captures something essential about time that remains true today. We live in time. We move through it. We feel it. We plan around it. But when we try to say what it actually is, language fails us. Is time a thing, like a river, flowing from future to past? Or is it a dimension, like length, simply there? Is it something the universe does, or something the universe is? Is it created by change, or does change happen within it? 1,600 years after Augustine, physicists, philosophers, and neuroscientists are still wrestling with these questions. We have built clocks of astonishing precision. We have bent time with speed and gravity. And we have looked back nearly to the beginning of time itself. And yet the simplest question, what is time, remains beautifully, stubbornly unanswered. Perhaps that is part of its wonder. Some questions are not meant to be solved. They are meant to be lived. Music exists only because time does. Think of your favorite piece of music. Not the lyrics, not the instruments, not even the melody. Think of the experience of hearing it. The way one note follows another, the way a chord builds and resolves, the way silence between notes can feel as meaningful as the notes themselves. Now imagine freezing a single instant of that music, one snapshot, one slice of sound, captured in a fraction of a second. What would you have? Not music, just a tone, a vibration, a fragment without context. Music is not made of sounds. It is made of sounds in time. It is the relationship between one moment and the next. The tension of a note held just a little too long, the surprise of an unexpected chord, the satisfaction of a resolution that arrives exactly when it should. Without time, there is no rhythm. Without rhythm, there is no melody. Without melody, there is no song. In a way, music may be the most beautiful proof that time exists. Not as a formula, not as a measurement, but as an experience. A reminder that time is not just something we endure. It is something we compose with, whether we know it or not. Every conversation, every walk, every evening spent doing nothing in particular. These are all compositions in time. Melodies played so softly we sometimes forget to listen. Sleep is time's quiet gift to you. Every night, something remarkable happens. On your conscious mind, that restless narrator that has been commenting on your life all day begins to fade. Your thoughts slow, your muscles relax, your breathing deepens, and without any effort on your part, you cross a threshold into a state that science still does not fully understand. Sleep is not the absence of wakefulness. It is a separate, active state, as complex and purposeful as anything your brain does while you are awake. During sleep, your brain replays and consolidates the memories of the day, strengthening the ones that matter and letting the rest dissolve. Your glymphatic system, a waste clearance pathway that is mostly inactive during the day, opens up and flushes out metabolic debris from your neural tissue. Growth hormones are released, immune functions are restored, damaged cells are repaired. All of this happens in time, but it happens in a time that feels different. Hours pass in what seems like moments. Dreams compress entire narratives into a few minutes of REM sleep. When you wake, the night has vanished, and you are, in a very real sense, a slightly different version of yourself than the one who fell asleep. Sleep is time's gift, a nightly reset, a pause in the story that allows the next chapter to begin fresh. And right now, as you listen to these words, that gift is waiting for you, patient and unhurried, ready whenever you are. This moment will never come again. Of all the facts about time we have explored tonight, perhaps the most quietly staggering is this one. The moment you are living right now, this exact configuration of atoms, this precise state of the universe, and this particular arrangement of your thoughts and feelings and breath has never existed before and will never exist again. The universe is 13.8 billion years old. It contains more particles than you could ever count. And yet, in all that vastness, in all that history, this specific moment is unique. Not approximately unique, not roughly one of a kind. Absolutely, perfectly unrepeatable. The air moving through your lungs right now has traveled through storms, forests and oceans before finding its way to you. The atoms in your body were forged in stars that died before the Earth was born. The electrical signals flickering through your brain at this moment form a pattern that has never occurred in any other brain, in any other place, at any other time. You are not just in time. You are a single, fleeting expression of it, a momentary shape the universe has taken, never to be repeated. And the fact that you are here right now, aware enough to wonder about it, is not just remarkable. It is, in the quietest possible way, enough. And now let the mystery of time gently fade into quiet wonder. We have wandered far tonight. We began with the small delays inside your own brain, the 80 milliseconds that separate you from the raw present. We traveled through the history of human timekeeping, from shadows on stone to atoms vibrating in laboratories. We sat with Einstein and felt time stretch and bend. We listened to the rings of ancient trees and the slow heartbeat of a 500-year-old shark drifting beneath Arctic ice. We compressed the universe into a single calendar year and watched all of human history flicker past in its final second. We looked back in time through starlight and forward through the slow dimming of the last black holes. We asked whether time is fundamental or emergent, whether the present is the only real thing, or whether all moments coexist in a vast, silent landscape. And we listened to music, not for what it said, but for what it proved. That time is not just a measurement, it is the medium in which beauty exists. Through it all, a single quiet truth kept surfacing. Time is not something that happens to you. It is something you are part of. You are not a passenger on a river of time. You are the river. Every cell in your body keeps time. Every memory you hold is a fossil of a moment that once was. Every breath you take is a small act of participation in the oldest process the universe knows. You are made of time, not separate from it, not struggling against it, woven into it gently, the way a thread is woven into fabric, the way a note is woven into a song. Tonight, as you rest, time continues. Somewhere, a bristlecone pine is adding another fraction of a millimeter to its trunk. Somewhere, a muon born from a cosmic ray is streaking through the atmosphere, living longer than it should because the universe bends the rules for those who move fast enough. Somewhere, the cosmic microwave background is washing over a quiet planet, carrying the faintest memory of the beginning of everything. And here in this small corner of the cosmos, you are lying still, breathing slowly, letting your thoughts grow soft. You are a brief and beautiful arrangement of atoms that the universe has assembled just once, in just this way, for just this moment. And that is not a small thing. That is everything. So wherever you are tonight, let your mind rest. Let the questions settle. Let time do what it has always done. Carry you gently without asking anything in return. The journey does not end here. It simply pauses, like a pendulum at the top of its arc, weightless for just an instant before the next swing begins. Sleep well. Time will be here when you return. It always is. Good night.